process management. Then I think we should finish that today. Then on the next lecture, on Thursday, we start on programming. Okay. So today we go on to process management. Right. So when we look at process management, we basically look at two situations, which are a deadlock and starvation. That is, those are the two which we'll be looking at: deadlock and starvation. So on the deadlock, that's where we will look at more things. We'll look at 7 cases of a deadlock, conditions necessary for a deadlock to be there, how do we model a deadlock, and also the different strategies which are used for handling deadlocks. Then we also look at how we can avoid the deadlock avoidance and detection, and also recovery. Then we also go on to look at starvation. We don't talk much about starvation there. So in other words, these situations are managed by the operating system as it synchronizes the processes, right? So it manages deadlocks and starvation. So if there is a lack of process synchronization, there can be a deadlock or a starvation. And when we talk about a deadlock, we are talking about a system entanglement whereby resources are being requested by a process, and you find out that that resource is also held by another process, which might also be waiting for another process that is being for another resource that is being held by the other process, right? So each job will be waiting for a vital resource to become available. Then the resources are also held by other jobs, which are also waiting to run. But then these jobs which are already holding other resources cannot run because the resources that are in their need are unavailable. And as a result, all the jobs come to a standstill. When we're talking about a job, in this case, we're talking about processes, right? That is what we talk about when we talk about a job. Then, to complete the resources are unavailable, then the deadlock becomes even conclusive if one of the jobs that is running also comes to a standstill, right? And there is only one way of resolving this, that is, there will be need for external intervention for the deadlock to be eliminated. So let's look at that situation, the traffic situation. All right. As you can see, let's say with this track there, right? Assuming that it is heading toward this direction, right? In its lane, right? But then because there's a deadlock somewhere there, this track can move. So these two also won't be able to move. When it stops, it means this set. I think let me change the color. So this set will also come and get blocked here because of this track, right? So what does it mean? It means this track will also block the way. So what does that result in? the traffic in this direction will come and stop here. Right? When they stop here, to complete the deadlock, these ones also will get blocked here. And so this will not pass there. So that becomes a deadlock. Right? So a deadlock is more serious than indefinite postponement of starvation because it affects more than one job. So if you realize that whatever blockage might have caused this track to stop, at the end, everyone always stops. So we saw that this stops, if these ones were moving properly, and these ones were also moving properly. But because this one is stopped, these will stop at that point, right? Now, it means even though these were moving properly, they will stop at this point, right? While this stops, it means these ones, although they were moving properly, they also stop at that point. So that completes the deadlock. No job can go to completion. That means no vehicle can pass, okay? Because those are being tied up, the entire system, not just a few programs, is affected. Resource, this requires outside intervention, either by operators or users, or terminate the job. So, going back to our traffic situation, what does it mean? It might mean that you might need someone to start controlling, right? Maybe if this is blocked, someone comes and stops these ones, right? So that this can pass, okay? If this can pass, at some point they should be blocked, then this can pass, right? If this can pass, after some time they should be blocked, and then this will pass. When this pass, that means this will also pass, right? So if there is no outside intervention, it simply means the deadlock will not be resolved, right? So what are the 7 cases of a deadlock? One may have a deadlock on file requests. We may have one in databases or dedicated device allocation, multiple device allocation, in spooling, disk sharing, or in a network. These are 7 cases in which a deadlock can occur. So what happens in file requests? So if a job can request and hold files for a duration of the execution, a deadlock can occur. So I just looking at a situation whereby a file is being requested, and then the process has been allowed to hold the file for its duration of operation. You realize that even if the job is looking for another resource, it will still be holding on to that file. Then any other program that requires file 1 or file 2 will be put on hold, right? So file 1 is being used by process number 1, right? And process number 2, and process number 2 is requesting file number 2. However, file number 2 has already been allocated to process number 1, and process number 1 cannot proceed without file number 1. So you realize that at the end of the day, it's a deadlock. None of these processes will progress. So the deadlock will remain until the program is one program is withdrawn or forcibly removed and its file is released. That means you might actually have to terminate program number 2 or process number 2, such that when file number 1, process number 1 requests file number 1, it is now available. So that is the external intervention which we are talking about in this file allocation. Then in a database, deadlock can occur if two processes access and lock records in a database. Right. Maybe you might not have experienced it, but let's say you open a file, let's say an MSA file, then you double click on the same file in order to open it. You might be told that the file is logged for editing by another user, right? Now, this can happen in your own computer, and you can resolve it by what? By closing the second instance of the file, such that it can run only one. But now let's assume that you are sharing this file. So user number one opens the file and locks it for editing, let's say. That means if you want to access file number one, you will not access it. So whatever you wanted to do, if it is dependent on the availability of file number one, it means you cannot proceed, right? So that 3 different levels of logging. One, the entire database can be logged for the duration of a request, or a subsection of the database, or an individual record can be logged, right? This is an important situation, though, that when someone is accessing a file, you can lock it, especially when you don't want the data to be played around with. The best way would be to log the files or the records until it is completely edited, or until the next person releases it. That also enables data security, right? And also it avoids what we call race conditions. That means when a file is logged, it can be accessed by one person until it is made available. So process number one accesses resource number one, locks it. Process number two accesses resource number two, locks it. Process one requests resource number two, by resource number two is logged by process number two. Process two requests resource number one, which is logged by resource by process P1. So at the end, none of the processes will proceed, hence it is a deadlock. Then there's also a deadlock in dedicated device allocation, right? That means if you have a limited number of dedicated devices like printers, plotters, or tape drives. Same situation occurs, but in this case, it will be a tape or a drive request. It caused a deadlock. Then there can also be deadlocks in multiple device allocation, right? Deadlocks can happen when several processes request and hold onto dedicated devices while other processes act in a similar manner. So in other words, we're just saying, as long as a process can request a resource, hold onto it, then it means at the end of the day, there will be a deadlock. Process number one requests the printer, right? Process number two has been allocated the printer, but it also wants the plotter, which has been allocated to process number three, which is also waiting for the tape drive, which has been allocated to process number one. Once you form this circle, the closed loop, then there's a deadlock. Then deadlock in spooling, most systems have transformed dedicated devices such as printers into a shareable device by installing a high-speed device, a disk between it and the CPU. So there's what is called the spooler, right? The disk accepts the input from several users and acts as a temporary storage area for all output until printer is ready to accept it. Okay, so that is the spooler that we're talking about. That. So it acts like a buffer. You send file number one, it puts in the buffer. File number two is put in the buffer. File number three, file number four, right, and the like, right. So they disable the output from several users, right? If the printer needs all of a job's output before it will begin printing, but spooling system fills available disk with only partially complete output, then the deadlock will okay. All right. So what it means is, for interest's sake, let's say the printer wants to print one complete page, right? But then process number one has just sent half a page to be printed. Process number two send half a page, and at the end they fill up this buffer, right? But then the conditions on the printer is that it needs a complete record in order to start printing. That means the printer will not print because the what it has received will be partially completed sections of the job, right? That's one of the problems that you can face in spooling. Then disk sharing. Disks are designed to be shared, so it's not uncommon for two processes to access different areas of this same disk. Without controls to regulate use of disk drives, competing processes could send conflicting commands and deadlock the situation, right? So process number one reads records at cylinder 20. Process number two writes to file at cylinder 310. Then you go on to the input-output channel, disk control unit, and then to the disk. Okay. So what will happen is, if you can't regulate, you might find out that this one wants to read on cylinder 20. Another process can read on cylinder 20. That is fine. But when one wants to write on cylinder 30 and another one also wants to write on cylinder 30, then if one starts writing, the other one cannot write until this one is complete, right? Then maybe it wants to write on another allocation which is being written to by another process. So at the end of the day, it cannot complete its writing because it is waiting to write through to another disk. So it will be circulating on this section. Then if that one also is waiting for another process to complete writing on the another space so that it can also write there and complete its job, then we'll get into a deadlock when they are sharing the disk. Then in a network, there can be congestion, right? A network maybe has filled the larger percentage of input-output buffer space. It can become deadlocked if it doesn't have protocols to control flow of messages through the network. So let's say the buffer for C6 becomes larger and filled, yet you wanted to maybe have access through that to C1, then it means this cannot proceed. If this one also needs access through C4, C4 is blocked by C6, then C4 automatically blocks C5, right? And so on and so on. That happens in the network. So for these conditions to happen, for the deadlock to happen, there should be some simultaneous occurrence of four conditions that the operating system could have recognized. One, there's what is called mutual exclusion. That's a necessary condition for deadlock. Two, resource holding, no preemption, and circular wait. These are the four conditions for a deadlock to occur. Let's look at them one by one. Mutual exclusion, we are allowing only one process to have access to a dedicated resource. That means if only one process can get access to the dedicated resource, then it means any other process which needs it will not be able to access it. Then resource holding, the act of holding a resource and not releasing it, waiting for other jobs to retreat. In other words, a process takes resource number 2 and it is holding it, waiting for other resources. In other words, it is anticipating the other resources to stop or retreat so that it can proceed. That is resource holding. Then no preemption. There's no temporary reallocation of resources. Once a job gets a resource, it can hold it for as long as it needs it. So it means once a process gets the resource, it can hold it as long as it needs that resource. That is no preemption. That means you have not temporarily reallocated resources. In other words, preemption will be that when the operating system sees that this had been running for some time with the resource, it can take it away from it. That will avoid the deadlock. But if there is no such algorithm to take away a resource from a process that is running, then a deadlock can occur. Then circular wait. Circular wait, we are saying, now that the other three conditions have been satisfied, then the algorithm is such that a process will wait for another process to release the resource. Itself, it will not release the resource, but it would wait and expect other resources to release the resource. That's circular wait, right? So in other words, every process that is running will be holding on to its resource in anticipation of another process releasing its own resource. That is the circular wait conditions. So when these four conditions have been satisfied or have happened simultaneously, then it means the operating system will get into a deadlock. That is what we are talking about. So how do we model deadlocks? We use what are called the directed graphs, right? So circles will be representing resources, circles will be representing processes, sorry, and the squares will be representing resources. So a line between the resource and the process will mean something different depending on the direction of the arrow. So if the line is coming from the resource to the process, it means the process has been allocated the resource and it is holding on to it. If the line is coming from a process to a resource, it means that the process is requesting that resource and is waiting for that resource to be available, right? So what are we saying? In figure A, resource 1 has been allocated to process number 1. In figure B, process number 1 is requesting resource number 1. So there is allocation here, there is a request in this case. So we are making reference to the process, right? So what happens? So it means resource 1 has been allocated to process number 1. Process number 1 is requesting resource number 2. Resource number 2 has been allocated to process number 2, and process number 2 is requesting resource number 1. Okay? So the arrow from the process to the resource shows a request. The arrow from the resource to the process shows allocation. That is how we allocate, we model our, deadlocks, right? So again, we are looking at this situation. Resource number 1 allocated to process number 1. In this case, resource number 1 is freed. That means it is completed. Resource number 2 allocated to process number 2. Resource number 2 released. Resource number 3 allocated to process number 3. Resource released. Right? But in this situation, resource number 1 still being held. Resource number 2 still being held. Resource number 3 still being held. Okay? So up to here, the situation is normal. But when process number 1 requests resource number 2, which has been allocated to process number number 2, which is also requesting resource number 3, which has been allocated to process number 3, which is also requesting resource number 1. This becomes a deadlock, right? That becomes a deadlock, right? Same thing here. Requests. This is an allocation. This is an allocation. This is an allocation. If we have them, on this request, this is a request, and this is a request, right? So how do we handle deadlocks? 1, prevent one of the 4 conditions from occurring. So the conditions which we talked about, right? Preemption, resource holding, circular weight, and so on. If you can avoid any one of those conditions, then a deadlock can be avoided. And the operating system can also, through its accounting mechanism, check processes and try to avoid a deadlock when it is imminent. It can avoid a deadlock when the deadlock is imminent. Or it should also detect the deadlock when it occurs and recover from it in a proper manner, right? So those are the ways in which a deadlock can be handled. So how do you prevent a deadlock? To prevent a deadlock, the operations might limit one of the 4 necessary conditions, but you know that the same condition can be eliminated from every resource. Why? Because like mutual exclusion is necessary in any computer system, because resources like memory, the CPU must be exclusively allocated to one user at a time, right? So you might be able to use spooling for some devices, and you might trade one type of deadlock for another case. So in other words, when one deadlock occurs, you might switch between the deadlock situations and see which one the system can quickly recover from, right? One can prevent resource holding or no preemption. Resource holding can be avoided by forcing each job to request at creation time every resource that it will need to run to completion. So in this situation, we are saying, as soon as a process is being created, its required resources are also determined and the requests are made there. However, this will reduce the degree of multi-programming, right? And also, peripheral devices would be idle because they've been allocated to a job even though they wouldn't be used all the time. For example, let's say a process will run and its end, it should print out something. So what it means is this process will be allocated the printer before it starts running, right? But then that means the printer can be idle for some time because maybe the printing is required at the end of the job, right? No preemption could be bypassed by allowing the operating system to deallocate resources from a job. And this is easy if the state of the job can be easily saved and restored, but it is bad if you preempt dedicated infrared devices or files during modification. So in this situation, we're just saying, when a process is running and is holding to a resource and it has been blocked by another situation, then the operating system can choose to take away that resource, give it to another process that will use the resource and complete. But then the operating system should be able to save the status of that process so that when that resource has been used, it can reallocate the resource to the process, and the process will start away from where it ended rather than starting from the beginning. The circular weight can be bypassed if the operating system prevents formation of a circle, right? So this can be by maybe numbering the resources, number 1, number 2, number 3, and the like, and force each job to request its resources in ascending order, right? Resource number 1 first, resource number 2 next, right? So in this case, the requirement is that the process should anticipate the order in which it will need the resources. So what does it mean? If it needs the 3 resources, then it says this is my resource number 1, this is resource number 2, resource number 3. So what it means is as long as it has not used the resource number 1, resource number 2 and 3 are still free to be used by other processes, right? Or it can be avoided. If the operating can remove one condition for deadlock, it can avoid one if the system knows ahead of time the sequence of requests associated with each of the active processes, right? This is the Bingas algorithm used to regulate resources allocation to avoid deadlock. So in this situation, there are 2 states, the safe state and the unsafe state, right? The safe states, it means the resources can be made available without interfering or stopping the operation of the whole system. There's an unsafe state, right? It may not lead to a deadlock, but it shows that it can give conditions for a deadlock to occur. This becomes an unsafe state, right? So we have the safe and the unsafe state in the Bingas or in Bingas algorithm. So what is the Bingas algorithm? It is based on the bank with a fixed amount of capital that operates on the following principles. So the principles in the Bingas algorithm: 1, no customer will be granted a loan exceeding the bank's total capital. 2, all customers will be given a maximum credit limit when opening an account. No customer will be allowed to borrow over that limit. And then the sum of all loans won't exceed the bank's total capital. So those are the principles that are used in the Bingas algorithm. Right. Then the operating system or the bank, which is now our bank, must be sure never to satisfy a request that moves it from a safe state to an unsafe state. Right? So the job with smallest number of remaining resources may not be granted access. Right? Why? Because the resources become exhausted, then we get into a deadlock. Right? That should be avoided. So that's okay. The situation, the safe state, customer 1 has taken no loan, 2 is been put at 4,000 maximum credit, and the remaining credit is to 4,000 because it's not taken anything. Customer number 2 is taking a loan of 2,000, but there's a maximum credit of 5,000. That means it still has 3,000 they can take. Customer number 3 takes 4,000, but there's a maximum credit of up to 8,000, and then the remaining credit is 4,000. So in this case, you can see that, okay, the maximum that the bank can allocate, looking at that, let's assume there's 3 customers so that we don't confuse anything. Then it means the bank can loan up to 17,000, right? Then it has already loaned out what? 6,000. So it is left with 10,000 which it can loan out, which means any one of those customers can still come in and get a loan. But what is the unsafe situation? Customer number 1 takes 2,000, and remains with 2,000. If you can take customer number 2, 3,000, remains with 2,000. If they can take customer number 4, take 4,000, remains with 4,000. All right. So the total that has been loaned is now 9,000. Right. And now the total capital fund of the bank is 10,000. So what does that mean? It means although the bank has said that it can give up to 17,000, in reality, its total capital fund is 10,000. So what was the assumption? The assumption was that the customers would not take loans that will come to exceed that. So it means it can only go up to that 9,000. The condition is no longer safe because it is only left with 1,000 to spare. Yet it's still, on the other side, the customers will still be demanding about 8,000 if they need a loan, but then the bank only at 10,000. So what happens is these customers, when they come back, they are not getting they're getting the loans until maybe one repays, and then the total loan maybe goes down to maybe 6,000 again, then they can give another loan. That is the Bingas algorithm that we are talking about. What are the problems now with the Bingas algorithm? If they enter the system, jobs must state in advance the maximum number of processes needed. But if you remember, when we're talking about spawning in terms of process creation, you realize that maybe when the process is running, it may look as if it will just need 1 or 2 resources. But on the other side, let's say it spawns another process. Let's say process number 2. Yet process number 2 needs some resources. You realize that now those resources, they might now not come in the anticipated order according to the first job that has been created. Also, the total number of resources for each class must remain constant, which is also not possible because of their possibility of spawning. When a job can create another job, then it will not necessarily mean that the resources will remain constant. It might require more resources as it progresses. And also the number of jobs must remain fixed. Again, a job can create another job. And so the jobs will no longer be restricted as such. Overhead costs you get by running the avoidance algorithm can be quite high. Resources aren't well utilized because the algorithm assumes the worst case. Right? It avoids deadlocks by assuming the worst case scenario. And this will mean that some of the resources are not fully utilized. And then scheduling will also suffer as a result of poor utilization, and jobs are kept waiting for resource allocation. Right? That's some of the problems that you can get with the Bingas algorithm. Then, how do you detect the deadlock? We use directed graph to show circular weight, which indicates a deadlock. Algorithm used to detect circularity can be executed whenever it is appropriate. So how do we reduce the directed resource graphs? 1, find a process that is currently using a resource and not waiting for another one. Remove this process from graph and retain resource to available lists. Okay. 2, find a process that is waiting only for a resource class that aren't fully allocated. Process isn't contributing to deadlock since eventually get the resource it's waiting for, it will finish the work and retain the resource to the available list. Go back to step number 1 and continue the loop until all lines connected resources or process have been removed. That is the process of reducing resource graphs. Let's see how that is done. So in our first situation, we have resource number 1 allocated to process number 1, process number 1 requesting resource number 2, allocated to resource number 2, requested by process number 3, allocated to process number 3. So if you look at that situation, process number 3 is not requesting any other resource. So since process number 3 is not requesting any other resource, it can use the resource and release it. So this has been released by resource number 3. Okay. So now our situation is now that we've allocated resource, then it's requested, it's allocated here, and it's requested. As you can see, there is no conflict between any processes for resource number 3. That means this situation can be removed again because process number 2 can get the resource. Since it has already been allocated resource number 2, it can go to completion. So this path is also cleared, right? And since process number 2 is also the one which is using resource number 2 and is not requesting anything else, it means it can also use resource number 2 and finish up. That makes resource number 2 available to process number 1. So process number 1 can also complete, right? Because already it has access to that. We have reduced our graph to this situation and we don't have any deadlock. So that might be an algorithm which can be used by the operating system in order to avoid any deadlock situation. Recovery. Once a deadlock has been detected, it must be untangled and system returned to its normal state as quickly as possible, right? So there are some recovery algorithms which are used, but you realize that all these algorithms require at least a victim, which is an expendable job, which will be removed to remove the deadlock. So how can we recover from a deadlock? One, we can terminate every job that is active in the system and restart from the beginning. This is a rather costly algorithm because we have to restart again. So in this case, when there's a deadlock, all processes are killed and then it starts afresh. Or I can only terminate those jobs involved in the deadlock, right? And they can be resubmitted. So instead of terminating all other jobs because there was a failure in the printer, you'd rather just stop the printer and let everything run, right? And all the other processes that are involved with the printer, then everything will run as usual. Or terminate jobs involved in the deadlock one at a time, checking to see if the deadlock is eliminated after each removal until it has been resolved. So what we have is in situation number 1, we terminate all, whether they are involved in the deadlock or not, are terminated. Situation number 2, as long as you are involved in the deadlock, you are terminated. Situation number 3, stop jobs one at a time until the deadlock is recovered from, right? So what does that mean? Job number 1, stop job number 1, check if the deadlock is not eliminated, go to the next job until the system recovers from the deadlock. Or you have a job snapshot or record, so that as the job or the process is proceeding, we know where it was, which resources were allocated, which were not allocated, and so on and so on. Such that as they proceed, and then there is, let's say, a deadlock happens, it means it is possible to interrupt it, roll it back slowly, and see which condition caused the deadlock, and then eliminate that condition. That's another way. Or select a non-deadlocked job, preempt resources it is holding, and allocate them to the deadlocked processes so it can resume execution. That's breaking the deadlock. So in other words, there's a process which is running, is not involved in the deadlock, but also has some resources there. Then the resources can be taken away from it, right? Then given to those which are in a deadlock so that they can complete. And then the deadlock will have been avoided, right? Or stop new jobs from entering the system, which allows non-deadlock jobs to run to completion so they will release their resources. In this case, there is no victim. That means when the deadlock occurs, you block any other new processes so that the ones which are running will also run to completion, which are not in the deadlock. Then after that, they release the resources, and then the others can also complete. So what do you do when you are selecting a victim, right? You select a victim, that is a process that is chosen for termination. You select a victim which has the least negative effect. So here you look at the priority of the processes. So high priority processes are not touched, right? So the CPU time is used by the jobs, and jobs close to completion are usually left alone. So what it means is the operating system will look at the jobs and see which jobs, if eliminated, will allow the program to continue, and also which jobs are not critical. But there are some critical jobs which, if they are stopped, they will stop other jobs. So the priority is being checked before this is done. Right? So the number of other jobs that would be affected if this job was selected as a victim. That's what I'm talking about. That job A is running yet, job B or C depends on job A. It would be unwise to stop job C or job A, because when you stop A, you've also stopped the B and C. And also programs that are working with the database deserve special treatment. So this is the issue of prioritization of jobs or processes. Right, so that's all about deadlocks, right? We'll look at questions after the next component, which is starvation. So starvation, it's a simple English, as you can see. When you say a process has been starved, it means the resource is never becoming available to the process. The resource is never becoming available to the process. We talk about the dining philosophers. You ever heard about them? If they're eating using chopsticks, and coincidentally you put the same number of chopsticks as the people, it means none of them will be able to eat because they will need 2 chopsticks. That's the dining philosophers. So if this one holds 2, this one holds 2, this one holds 2, this one will not eat. Right? That is what? Starvation. So you avoid starvation using some algorithms which detect starvation, right? So you have to detect if a job is being starved. right? Or has been waiting for long before the resource has been allocated. That is how it detects starvation. So these are the terms which we have looked at. You might need to go around, look at them, and also read more about this. Avoidance, deadlock avoidance, circular weights, that's a condition for deadlock, the deadlock, deadly embrace, we are defining a deadlock, deadlock detection, directed graphs, those which we use to model deadlocks, then locking of resources, mutual exclusion, no preemption. You can see that this and that are conditions for a deadlock to happen, prevention of a deadlock, process synchronization, rest conditions, resource holding, safe state, and the unsafe state, Bingas algorithm, spooling, starvation, victim. Those are some of the terms which we use there when we are describing process management in terms of deadlocks and starvation. So that leads us to the end of this lecture for today on resource on process management. So meaning to say the next lecture we'll be looking at programming. So I'm stopping the recording. Then